Yeah, so the next speaker this afternoon is Paquette from Oxford, who is doing his survey on topological quantum computing with anyons and use category theory there.
Yes, so after this orgy of n categories and beyond, I'm going to speak of just flat categories. Topological quantum computation with anyons. So the program is a bunch of words at least. Yeah, okay, so here's the outline. So yeah, I'm gonna give a brief outline of quantum computation. Gonna speak of anyons. I'm gonna explain these are in fact exotic quasi-particle living in a two-dimensional world. So I'm gonna explain why does it make a difference when we are considering particle in a two-dimensional world. I'm going to speak of modular tensor categories, but in a nutshell, we'll go really fast over it because the definition is quite long, very rich. I'm sure you can do it on your own. And I'll finish with topological quantum computation with anyons. So starting from quantum computation, so a classical computer is a device that operates on state built from strings of bits. So, so the state of a classical computer is just an element of Bn, where B is just 0 or 1. In contrast, now quantum computer work with a set of qubits or normalized vector psi in C2. This funky symbol for those who know is ket psi. Yeah, and which is a vector in C2 which is normalized. So 0 and 1 there are orthonormal vector forming an orthonormal basis called the computational basis of my state space. Now, if I consider a system of n qubit, I will take it will live in a state space C2 tensor, C2 tensor, C2 n times, and the system of n qubit will be described as a normalized vector to the space. So written like this now, where x, the cat x there takes value into Now, again, as an analogy between the classical and the quantum case, on a classical computer, transformation between states are taken as function from Bn to Bn, while in the quantum case, there are unitary transformation. And finally, if some state psi, which is a qubit in that case, alpha 0, ket 0 plus alpha 1, ket 1, in C2 is measured, then the probability of observing I, which is either 0 or 1, is given by the square of the amplitude of alpha I, which is, of course, equal to bra psi pi psi, where P0 or P1 are projected into the one-dimensional spacespan by 0 and 1, respectively. Now, okay, as we'll see later, quantum computing with anyon gives us access only to a finite set of unitary gates or transformations that one can apply in this system. And this might be the case even in regular quantum computation, or rather non-anyonic implementation of a quantum computer. So what happens if we actually just have access to a finite set of them? Because we'd like, of course, to be able to simulate at least all possible unitary transformation that we can apply in a qubit. So a set of unitary transformation is said to be universal if any unitary transformation can be simulated as a finite sequence of transformation from that set. Universal set can be exact if we can, of course, simulate exactly any unitary transformation or approximate it otherwise. So as a first theorem, the set of all one qubit transformation, which are 2 by 2 unitaries, together with a control knot map, which is this matrix there, is exact universal, which basically means that we can, on a string, which basically means that we'd be able to simulate any possible unitary transformation in a set of n qubit if we have access only to these gates. Now, the set of all 2 by 2 unitary transformation is an infinite set, and as I said, when we're going to speak of anyons, we'll just have access to finite number of transformations or unitary transformations, so we need to clarify the notion of approximate universal set. So transformation V will approximate U up to an accuracy of epsilon if u minus v applied to psi, the norm of that is strictly smaller than epsilon, that for all psi. Now by the Solovay-Kitaev theorem, we know that if a finite set G contained in SU2, which contains its inverse and such that the set generated by G is dense in SU2, then any one qubit transformation U can be approximated by a composite of gates from G, and this string of transformation is actually reasonably small. So from which such a set G together with the control nut is approximately universal. So is that clear? It was rather technical, but I mean it's going to be quite important because we're going to just have access to a finite number of unitary transformation, but we will want to be able to do anything we want with a set of anyons. So is there any question about that? No? Good. So anyons. Then enter the core and the interesting part of the subject. So what happens if we exchange two undistinguishable particles in 3 dimensions? So depending whether these two particles are bosons or are fermions, we have psi1, psi2 is equal to plus or minus psi2, psi1. Of course, we're going to have minus if we have a fermion, and we have a plus if we have two bosons. In both cases, of course, two successive exchanges will lead to the identity of the space of the two particles. Now we can think that in terms of paths. So two particles moving from some initial configuration to some final configuration leads to two different scenarios. We have two different classes of paths that can give that, either the direct or the exchange. Now we can fix one of these two particles at the center and just consider the movement of the second one relative to the first one, right? So in the first case, I have the direct path. So in fact, the first particle just move in some sense, and it will never. Oh yeah, sorry, I forgot to say that. So I consider one of the two particles which is fixed at the origin, and I consider that the two particles cannot be at the same place at the same moment, of course. So the first one is the motion of the second particle relative to the first one, which is a direct path, and in the second case, it's going to be an exchange. So from this, we see again that a double exchange yields a path that can be contracted to the direct or trivial path.
What's going on in those pictures? I mean, so one thing is staying at the origin.
Yeah, so the thing is that basically...
I can't see what the arrow pointing away from the origin do.
Well, yeah, well, it's the position vector of the second particle relative to the first particle, right? Was that... Yeah? Okay. Now, what occurs in 2 dimensions? So we'll consider that... that these 2 dimensions are spatial and time flows in that direction, down to up. So I can, of course there are more classes than that, but I'm just going to depict 3 different classes of path. Well, first there is a direct path. Second, there is the exchange. Third, there are 2 successive exchange, and I could picture 3 and 4. And why is that different from the 3-dimensional case where, well, again, I can pass into, by fixing one of the 2 particles at the origin and considering the movement of the second relative to the first one. So this is the direct path. Now I have an exchange. Now I have 2 successive exchange. But what's the difference with this and the 3-dimensional case? Well, of course, I cannot continuously contract this path, okay, to the trivial one, right? So these are really 3 genuinely different classes of path. So, in fact, in 3 dimensions, I'm going to have an infinite number of classes of path, right? And of course, I could turn also in the other direction. So is that clear, the difference between 2 and 3 dimensions? Yes? Okay. Oh, now it works. Interesting. Okay. No, the other way around. Yes. Okay, now after some tedious calculation using path integrals, one can verify that for such quasi-particles, works just too well now. Sorry.
It's the receiver at some position.
Okay. Well, that was an interesting talk, isn't it? Okay. After some tedious problems with the slides, one can verify actually that for two such quasi-particles living in 2 dimensions, now if I exchange psi 1 and psi 2, I'm going to obtain e to the I theta psi 2 times psi 1. Of course, this is more general than in 3 dimensions, since in 3 dimensions I can have just plus or minus there. Now, as the theta there in e to the I theta can take any value, such quasi-particles are called anyons. Right? The term was coined actually by Frank Wilczek before that. Yeah.
It's a question. It can take any value, but the value still is fixed for a particular situation.
For a particular family of anyons, yes. Yeah. Actually, I'm gonna tell you later on in the talk how to. Well, I'm gonna indicate how you can possibly calculate that. Not show you how to actually do it because it's quite tedious. But yeah. Okay, now the movement of anyons in 2 + 1 dimensions is encoded by the Braid group, which can be described by given some generators, which satisfies some equations, which I guess are better illustrated. So, of course, so the first equation, what does it say? It says that if, first, so again, if I consider that time flows from the bottom to top, so if I exchange I and I + 1, and then I exchange j and j + 1, this is the same thing as first exchanging j and j + 1, and then exchanging I and I + 1. The other one is a bit more obscure, but anyway, you can convince yourself, I guess, that you can continuously deform the first picture to the second one without crossing two strands together, right? So, yeah, another important point to make about anyons is that these quasi-particles arise as collective excitations of other particles. So if we let them get close enough together, these anyons will fuse into a single anyon. So now a little word, I'm not a physicist, but I guess I can explain in broad terms how anyons arises. So the thing is that you take a very thin slate of metal, you lower the temperature, and then you pass some electric current in that sense. So at some place, if there is an impurity into your slate of metal, the electron will start swinging around this impurity, and this will constitute actually an anyon. So of course you can move this impurity, and this will actually make the movement of your anyons. So the thing really is to think of these as flux tubes. So of course if I get two impurities, and I let them go close enough together, then my electron swinging around will start to behave as another collective, yet another collective but single excitation, which will give me another anyons. So now, what particular algebraic structure do we need in order to describe a system of such quasi-particles? We need modular tensor categories. As I said, I think it's better explained via an example. We'll take a simple case of such modular tensor categories. But I will go quite fast over the algebraic structure. So first, of course, we need a system of label or type that will represent the charges of our anyons. So what is the charge of an anyon? Basically, it's just really, think of it as a label. Over some particular anyonic model, I can have many different charges. I'm going to have a trivial charge. I'm going to have a negative charge for a charge. So it's probably a way to actually call it a charge. But of course, this will be just the object of the category. We need a way to express a compound system of anyons. I will express this by a monoidal or tensor structure with a trivial charge as the tensor unit. This category is usually not considered strict because the bracketing will just tell me in what order, this will become clear later, but in what order my anyon will ultimately fuse. Because fusion as I explained in the previous, or two slides ago, is really the way we actually measure the charge of a system of anyons. Okay, the word line of a system of anyons are rather described by representations of the Braid group. Will require that our monoidal category has a Braid structure as opposed to being symmetric. We need a way to express the notion of conjugate charge. So for a given charge A, I will have a conjugate charge A star, which is the unique charge which can fuse with A to yield a trivial charge. So the structure that captures this notion is called a rigid structure, which is really a compact closure, but for a non-symmetric case. The fact that the objects we're looking are extended object or flux tubes means that in general representing their movement graphically with strands in 2+1 dimensions is not enough. Actually what I need is a ribbon structure. I will not go into this technicality for now. And now, formal way to express the fusion rules and to map all the preceding algebraic formalism to the context of Hilbert space is taken care via a semi-simple structure compatible with all the preceding structure. Of course, this will entail some sense that my category is enriched over Hilbert spaces, and it's really a functor that will make the passage from the modular tensor structure to the Hilbert space structure. But in particular, semi-simplicity captures the following idea, is that the charge of an anyon is elementary. I mean, it cannot be decomposed into other elementary entities. In categorical terms, the charge of an anyon has no other sub-object than itself, and that the set of endomorphism of a charge, a simple object, is isomorphic to the complex field. Finally, but importantly, this entails also that given two different simple charges, any two, S1 and S2, which are different, where S1, is not equal to S2, the offset between S1 and S2 is trivial. Yeah. So a category with all these structures is called a semi-simple modular category, and as I said, it's fairly long to define details, so I'll skip the details, and I'll go straight to the simplest example of such a category. But anyway, I just wanted to go through just to tell you in a more general case that the one I'll expect, what we actually expect from a system of anyons. Any questions?
So you said that the conjugates, when you tensor with the conjugate, you get the identity, or you get?
No, you don't get the identity, but I mean there is some special map to which you can consider the fusion to which will yield to the trivial charges. Anything else? Okay, now. Quantum computation with Fibonacci anyon. This is actually probably the simplest case of a modular tensor category. So yes, we'll actually show that with these anyons, we can actually obtain a universal set of gates, so which means that basically we can simulate any possible quantum computation with these anyons, which are unfortunately doesn't seem to be able to be simulated in the lab, but anyway, it's a cute model. So let's have a look at it, and it will illustrate all the theory I've given so far. So yeah, okay, so I'm going to start with the fusion rules of Fibonacci anyons. So Fibonacci anyons are quite simple, really. So I have only two different charge, which is 1 and tau. 1 will be my tensor unit, and tau will just be a non-trivial charge. Both are their own anti-charge, which means that T star is equal to tau star is equal to tau, and 1 star is equal to 1, and they satisfy the following fusion rules. Well, the first one are quite trivial, right? Because 1 is the tensor unit, so 1 tensor 1 is iso to 1, 1 tensor tau is iso to tau tensor 1, which is iso to tau. But the interesting rule, which will make all the difference, is that tau tensor tau is equal to 1 plus tau. Okay, what does that mean? This means basically that you consider this as a space-time diagram in some sense. Okay, so I have two different anyons, which can be either of charge tau or charge 1. At some point, it will actually fuse together, and I will get another charge. Okay, so if these two anyons are of charge tau, and they actually fuse together, okay, they can fuse either. This is what my third charge says. My third fusion rule says is that if I have the compound system of two anyons of charge tau, if it fuses, it actually yields an anyon of charge tau, or just my direct sum there, 1, which is the tensor unit. Okay. Now, the two other rules just says that if I have an anyon of charge tau and I let it fuse with something of the trivial charge, well, it will give me an anyon of charge tau. Right? So this is pretty much what I said. Okay, now back to our model. Okay, now I will consider 3 anyons of charge tau. Now I will draw this as that. Suppose that my little dot or my anyons are all of charge tau. I have a set of 3 anyons. Okay, I can consider the fusion of 2 of these anyons, and then consider the fusion of the output of the fusion of the 2 first with the third, which basically is tau, tensor tau, tensor tau. Like this. So this is, well, it's the equation that I've written just up there. So if I let these 2 anyons here, or these 2 actually fuse, it will give me either 1 or tau, right? Now, the tensor product distributes over the direct sum, so I get 1 tensor tau plus tau tensor tau. 1 tensor tau is tau, okay? And now, again, by the fusion rule, tau tensor tau is isomorphic to 1 plus tau, okay? So, up to a rearrangement of term, the thing up left is equal to 1 direct sum 2 times tau, which is really just tau plus tau. How should we read this? We should read this: the diffusion process of 3 anyons yield the final charge tau in 2 different ways, or 1 in a single way. Right? Is that clear?
Is there any room for talking about probabilities? So if tau tensor tau is isomorphic to 1 plus tau,
No, not that.
there's no room.
Not at this level.
Right.
Because as I said, like Hilbert spaces are rise via enrichment, and I really didn't spoke about sets yet, so there is no probability at this level.
So it's not like if we actually did this experiment and we had these 2 charges and we let them fuse and then we checked what was there, there'd be a 50% probability
I didn't
we
define
get.
the notion of state. There is no state there. I just suppose I have 3 anyons, I let them fuse, and this is the combinatorics to actually give me. Okay? It's going to be the first terms of the Fibonacci sequence, actually. So in that sense, right? Okay? We can continue. If you put another tau, we can get other terms of the Fibonacci sequence, etc. So, okay. Now, I'm going to represent this as fusion diagrams. Okay? So I start at the bottom. Again, times flow from bottom to top. Here, so I get 3 different anyons of charge tau. So the 2 fuse together, so it can give either a tau or it can give a 1. So here I have my 2 scenarios. Now I can let these 2 things fuse. So my first 2 terms here, as a result of the first fusion, I have a tau. So tau fusing with tau will yield another tau or an anyon of charge 1. Okay? So these are my 3 scenarios. As I said, there are exactly 2 ways I can have tau as a charge here, and 1 way in which I can obtain a 1 after the first fusion. So this is quite important, right? Because these, or rather the dual of this diagram, will form my basis for my state space. So is that clear? So the thing is that here I have really like these 2. Okay, so for a final charge tau, here I have 2 different degrees of freedom, which means that the first fusion is either 1 or it's tau. So it's going to give a 2-dimensional complex Hilbert space, which will actually simulate my qubits. Rather, the third one, where I just have 1 degrees of freedom, is going to be a 1-dimensional Hilbert space, or rather just a complex field, which is just a non-computational state. Now I'm going to enrich, as I said, it's because the category is actually enriched over a finite dimensional complex vector space via this splitting space. Again, okay, so let me just use B as a placeholder here. I consider my triplet of anyon, tau tensor tau, bracket tensor tau. I know that this is equal to that. Now, okay, I can factor out the sets B to 1, O plus B to 2 times tau. And since 2 times tau is equal to tau plus tau, again, I can factorize the 2. Now, since, as I said, the semi-simple structure here entails that for different S1 and S2, where S1 and S2 are simple, in this case, either 1 or tau, so we have that the set between S1 and S2 is equal to 0, and since for any S, either 1 or tau, the endomorphism of S is isomorphic to the complex space, okay? If I set, it was a mistake, B actually equals to 1, okay? So this set, the set from 1 to 1 will be the complex field, okay? And the set between B to tau is going to be 0. So this thing here is going to be equal to CO plus 0. If I set B equals to tau, then this is the first term that goes to 0, and this one is a two-dimensional complex space. Right? This is how, Hilbert spaces arise in this context. Questions? Okay, so from this we conclude that considering the space of state with global charge S in 1 or tau is the same as considering this thing, right? And we'll just go back a few slides to explain this. So if I consider that my final charge here is tau is the same thing as considering that the global charge using, for instance, this diagram here is tau, considering that my three charges here are tau, and that the global charge, or rather the final charge is tau, then these two things here can fuse in two different ways, either 0 or, 1 or tau, and this will actually be a two-dimensional complex space. Okay, these, just a little technicality. This term, such as consideration, of course, fixes either the splitting space C, as I just said, or C2, which are orthogonal subspaces of C3, the topological space representing the triplet of anyons. Okay, so it will be within this topological space, or rather within the two-dimensional complex space that will simulate our qubit. And so now I actually need to speak of unitary transformation to say how we're going to act on our qubits. But before, okay, it's worth stressing that it makes 3 anyons to actually simulate the qubits, right? Let's take 3 of them charged tau. Okay, this is reminiscent of the fact that we actually encode our information to global or topological degrees of freedom. Okay, so now we're going to extract the unitary transformation. So in order to ensure the consistency of the model Fibonacci, splitting has to be associative, as expressed categorically via some instantiation of the Pentagon axiom from the monoidal structure. So there are 2 distinct splitting spaces that can be obtained from a triple of anyons, i.e. the bracket tau tensor tau, or tau tensor bracket tau tensor tau. Of course, I can rewrite this using some splitting diagram. So the thing is that really I can think of this as basis vector, right? So this would be just a matrix equation, taking this thing here, summing over the b's there, okay, onto this. So this is just a question of actually considering this as a matrix equation if I consider this splitting or fusion as basis vector or their dual. Now, recasting the pentagon axiom in this context leads the following really nice diagram. So I guess, do you recognize the pentagon axiom here? So just think about bracketing. So this is the bracket of S tensor T, tensor the bracket of S tensor T and U, tensor V. Okay, so here I apply fusion just over the sub-triple here, and I leave the one which is dotted alone, which will give me this configuration of anyon, which is equal to this thing, so I leave this part alone. I can apply F. So really this is just an instant of the pentagon axiom that we find in monoidal category. Now, okay, looking at different scenarios of fusion, I can equate both sides of the diagram and this yield another very ugly matrix equation. Now if I solve this in conjunction with a given set of fusion rules, okay, this will yield the called F matrix or fusion matrix, which actually passes from one possible configuration of fusion to the other configuration of fusion. As I said, the thing is that we can consider each fusion diagram which makes sense with our fusion rule as basis states. So this thing is that this F matrix is going to actually be a unitary transformation between two possible fusion scenarios. Now I can solve, so in Fib for a triple of anyons of charge tau, the trivial charge can split into such triple in only one way, as we've seen a few slides before. In this particular case, the F matrix is just trivial, it's 1. Since the first splitting is coerced to be tau tensor tau. Conversely, if the initial charge is tau, then of course I have 2 different degrees of freedom, and the splitting process can occur in 2 different manners. So in order to get the F matrix, we solve this equation there with the different possible values and possible fusion scenarios that make sense. So trust my word on this one, which actually makes sense. The thing is that really, the thing is that really we exchange values. So S, T, and U, and V, and W here are going to be different charges. So if S and T fuse at some value, and then it's going to fuse with the value that I fix for U to B, and etc. So I just go over all possible value. This is what I was saying when I was saying it was quite complicated to actually solve. But this is unfortunately how we do it, and no, there is no more elegant way to actually do this. So anyway, doing all the details, I want to actually obtain that F, together with the fact that yes, as I said, F is unitary, we obtain this matrix at the end, which is a unitary 1, and phi is the golden ratio. So now, this is the matrix that actually acts on the 2-dimensional subspace of my of C3, okay, and the other one, the one here, is acting in the 1-dimensional of C3, which is the topological space of my triple of anyons. So putting the 2 together would actually give me this. Okay, this matrix is again unitary. The lower right block, as I say, induces a change of basis on the 2-dimensional splitting space, in which I will simulate my qubits, while the upper left block is the trivial transformation on the 1-dimensional splitting space. Now we express what will be the consequence of exchanging 2 anyons on the splitting space. As such, an exchange is represented categorically by braiding. This will yield a representation of the braid group on the splitting space. So I can redo pretty much the same game as for the F matrix, but instead here I will consider an R matrix which will actually braid S and T into T and S, or the other way around. So again, instead of using the pentagon axiom, we're going to use the hexagon axiom, pretty much in the same way that we actually worked out the fusion for the F matrix. Here, we're gonna solve, since we already have the F matrix. Here we're gonna solve for the R matrix. this will give me the matrix, the unitary transformation that actually, which correspond to the effect of braiding like the two first anyon. So again, writing this as a matrix equation yields this ugly thing. And for a triple of anyon with charge tau, explicit calculation will yield this thing. Okay, such a diagonal form is not at all surprising. The thing is that, as I said, the set of transformation between S1 and S2, when S1 is different from S2, is actually trivial, it's 0. So the thing is that, of course, if I exchange these two anyons here, for instance, okay, I won't charge the charge of my couple of anyon there, right? So that's why this matrix has to be diagonal. And now, so the R matrix provided in the previous section give us a way to exchange the two leftmost anyons in a set of 3. I would like to know how do I exchange these two anyons. Well, of course, first I will apply the F matrix. After I will braid these two things. And after I will reapply the inverse of the F matrix at the initial. So this is what I just wrote, which will give me the B matrix. Which corresponds to the unitary transformation, which correspond to exchange the two rightmost anyons in my triple. Okay, so there's a way to initialize a qubit, which is actually to consider a splitting of a set of anyon. Okay, and this will be a base vector in a two-dimensional subspace of the topological space of a triple of anyons. We have both the R and the B matrices as unitary acting on such subspace, on the two-dimensional subspace. Okay, so the goal now is to show that this is enough to describe the universal set of gates. Yeah. Okay. So the basic idea now to simulate quantum computation, so full-fledged with anyon, is given by the following facts. So first, we consider a compound system of anyons. We initialize the state in the splitting space by fixing the charges of subset of anyons according to the way they will fuse, which basically means that here I've got two different taus. Okay. So if I let them fuse, I just don't know if it's going to be a tau or 1. So actually, by moving an anyon around, performing some measurement in some sense, I will fix that to be either 1 or tau. And then, this way I can actually fixes the global charge of my whole set of anyons, so, and all intermediate charges, which will give me a basis state in which the computation starts. After I will braid my anyons, and finally I will let the anyons fuse together, and the way they fuse will determine which state is measured, and this constitutes the output of the computation. In fact, we are quite lucky in this case. The set of R and B matrices and their inverses, the representation of the inverse braiding, right? Because if I can braid in some sense, of course I can braid in the other sense, and this is the exact inverse of the, if I think of these braids as a unitary transformation in my fusion space, of course if I braid in the other sense, it's the exact inverse of it. And it is dense in SU2, which means that it satisfies the condition of the Solvay-Kitaev theorem. So to get an approximate universal set of gate, it just remains to construct a controlled NOT gate. So we'll do so following the works of Ponxtia et al. Any question so far? Or? Okay, the idea is relatively simple. So start with two different triplets of anyons. We'll need to intertwine a pair of quasi-particles from the first triplet, which is the control pair, with the target triplet without disturbing it. As the braid operators are dense in SU2, we'll arrange such an intertwining so that its representation in SU2 will be close enough to be identical. The next thing, of course, will be to implement a NOT gate by braiding our two anyons of the control pair with those of the target triple. And finally, we will extract the control pair again without disturbing it. You're going to see doing this will actually illustrate the difference between the topology and what actually happens in the Hilbert space quite strikingly, I think. And it will also produce our control NOT gates. So the key point to remember, braiding involving the trivial charge 1 with any anyon really does not change anything, right? So of course the trivial charge. So if I take two anyons and one of them is of the trivial charge, if I braid this trivial charge around it, it won't change anything. Thus, if I take two anyons, okay, of charge tau, and another anyon of charge tau, so I take three different anyons. Okay, this is not how we will construct the NOT gate, but this illustrates what I want to show. So the thing is that I can consider this pair here as a single anyon, because at some point they will fuse together. Okay, so I take this pair and actually I exchange and I re-exchange. Now if I let these two anyons here fuse together, and this gives me the trivial charge, charge 1, actually I haven't done nothing on this tau. But if it fuses as tau, actually the effect of the braiding will be taken into account in the computation. This is the idea that we're going to use to actually simulate a NOT gate. I don't ask you to understand this, but I just wanted to draw it so that you can appreciate the complexity of the braiding, which actually due to implement an identity. But yeah, so this is the idea. But the thing is that, look at the two different configurations, right? So I've written that in different colors. So it is an identity over the Hilbert space. That's right. Okay, so if I apply all these transformations here, it is an identity on the Hilbert space of these three anyons. However, topologically what happened is that I took this anyon here and I inserted it here. Okay, but the effect is trivial over the Hilbert space. Okay, now, now we can implement an I NOT, or NOT if you want, as the following braid. Now, I changed nothing in the topological configuration. However, on the Hilbert space, on the topological Hilbert space of these three anyons, I actually implemented this gate. This is a unitary transformation in which I actually applied. Yeah, okay, I didn't say that, but I mean, these gates are approximated with quite good. Okay, now finally, this is how I will implement my controlled NOT gate. So I will take this couple of anyon here, I will insert it here using the first implementation that I shown you. Okay. Now I will apply the NOT. After I'm going to apply the inverse, the topological inverse of that thing, I'm going to extract it. So on the Hilbert space of state, this is an identity, this is a NOT, and this is an identity again. So the thing is that at the end of my computation, I'm going to measure these two anyons. If it gives me a 1, okay, then I did not apply the NOT. If it's a tau, I did apply the NOT. So the thing to consider is that really this is a controlled NOT gate, and this is my control. This is my control qubit, and this is my target qubit. So now I have a set of two gates with their inverse, namely the R and the D matrix, which is dense in SU2, and I have a control NOT gate. So all these together actually forms. All this together actually forms a universal set of gates. So yes, I mean this is enough. So in conclusion, using such anyons, Fibonacci anyons, we can simulate a qubit. We can approximate any unitary transformation on a set of qubits, and we measure the system using fusion, from which we can simulate quantum computation with anyons, which is what I wanted to show today. That's it.
Any questions, comments?
You briefly mentioned that these particular anyons cannot easily be geometry, any idea why, or
These particular, I mean, the statement was nice because I wanted you to keep interested in the talk. I mean, actually, yeah, it's a bit harder than that. So what actually happens is that there are two different families of anyons. There are the so-called abelian anyons and non-abelian anyons. Fibonacci is a case of non-abelian anyons, in the sense that tau, if I fuse two different anyons of charge tau, it gives either charge 1 or charge tau. So this is non-abelian. It actually induces non-trivial transformation when I braid two of these anyons. In the case of abelian anyons, if I let them fuse together, it gives only one charge. Okay? And now these are actually simulable in laboratory, but they didn't manage to actually simulate non-abelian anyons. They are pretty sure that it's doable, but they didn't manage to do it. But yeah, something that I actually didn't mention, so why are we interested in topological quantum computation, I shall say, is that one of the main difficulties in quantum computation, of course, is the question of implementation, right? The things that quantum information decoheres really rapidly. So if I encode some information to some qubit, well, it gets just destroyed by the environment or something after a very short time. But the thing is that here, we actually encode the information to global degrees of freedom rather than local ones. So the thing is that this information actually is much more coherent. So that's why it would be a good candidate for the implementation of a quantum computer, much below the little remark that I just made. Yeah. And it's a cool thing. It's actually an applied application of category theory, right? So, in some sense. Okay. Yeah.
Just to follow up on this question, you mentioned that you can do abelian anyons.
Yeah.
Can these actually do quantum computation, or can you
No.
classically simulate?
No, it's behaves basically as a classical system, sort of. Yeah. Because you know it's going to fuse, right? So the thing is that when you're going to exchange these two, it will just change by global phase, which is, I mean, just jump in terms of.
Shall we go back to sketching?
Yes.